Okay, differences between class A, B, C and AB power amplifier. Serial number, parameter, class A power amplifier, class B power amplifier, class C and class AB power amplifier. Number 1, drain current. The drain current is for power A is ID is equal to IDC plus IRF sin omega naught T, and whereas ID is equal to IRF into sin omega naught T. For C amplifier, ID is equal to IDC plus IRF sin omega naught T. For AB amplifier, A or B current should be taken. Next, output voltage. V0 is equal to minus IRF or sin omega naught T. Vout is approximately equal to IRF by 2 into R sin omega naught T. VDD is equal to IRF into R by 2 pi into 2 phi minus sin 2 phi. A or B output power. So PRF is equal to I square RF R by 2. P naught comma max is equal to V square DD by 2R or A or B. Conduction angle 100% of the time, 50% of the time for class B and 0 and 50% of the time for class C. And class AB power amplifier 50% per time should be in the range of 50 and 100%. VI characteristic graphs are shown in the following for class A, class B and class C power amplifiers. Parameter, efficiency, figure of merit and applications. So eta is equal to PRF by PDC. Efficiency eta is equal to 50%. For class B amplifier, eta is equal to 78.5%, eta is equal to 100%. Figure of merit, Pn is equal to PRF by VDS into PK ID comma max is equal to 1 by 8, and for Pn is equal to 1 by 8. Pn is equal to 0 where phi approaches to 0. Pn between A and B. Applications, audio amplifiers, RF amplifiers, audio amplifiers and RF amplifiers. RF power amplifier design examples. We want to design a linear amplifier for use in a 1 to 1 GHz communication system. General power amplifier model should be like this. Design examples. We want to design a linear amplifier for use in 1 GHz communication system. The requirements are to supply 1 watt into 50 DC power supply is available. We must specify important device parameters, compute all component values and estimate drain efficiency. We will make arbitrary assumptions about the minimum values of VDS in the on state to simplify design procedures. And class A amplifiers. If the supply voltage is large enough to allow 1 volt 1 watt to be delivered the load without an impedance transfer methods. Pmax is equal to V square DD by 2R, that is equal to 3.3 whole square by 2.50, that is equal to 0.1 watt. The supply voltage is not nearly sufficient, so an impedance transformation is required. The maximum value of the transfer mode resistance is with a 4 ohm load, the peak RF current will not be exceeded. VDD by R is equal to 825 milliamperes. And the DC drain current bias must be set to approximately this value. If we assume that 1 watt is in fact ultimately delivered to the load after all losses have been taken into account, the drain efficiency would then be eta is equal to P naught by PDC is equal to 1 by 0.825 A dot 3.3 volts, that is 37% efficiency. So efficiency is approximately equal to 37%. Therefore, when the amplifier is supplying that 1 volt to the load, the transistor will be dissipating about 1.7 volt. So the packaging and heat sinking must be designed to keep die temperatures acceptably low with this dissipation. We need to specify component values for the output filter and for matching network. Let the output filter is a simple parallel RLC or parallel LC and having Q is equal to 10. Let the output filter is a simple parallel LC and having Q is equal to 10, bandwidth is equal to 100 MHz, center frequency FC is equal to 1 GHz, the resistance of L and C is equal to 5 ohms, hence XL is equal to 5 and omega L is equal to 5. XL is equal to 5, that is equal to L is equal to 5 by 2 pi into gigahertz is equal to 0.80 nan h. And next xc is equal to 5 by omega c is equal to 5. Then xc value is equal to 5, then j omega xc, that is equal to 31.8 picofarads. Class A amplifier design examples. Recall that at resonance, each reactive element in the parallel tank circulates an RF current that is Q times as large as that flowing in the load. Hence, the L and C must be able to withstand 2 amperes of peak current flow in this particular design. For RF choke, we wish its reactance to be at least about 10 times as large as the 4 ohm resistors of the tank at resonance. We must now provide a DC blocking capacitor and an impedance transforming network, and these functions may be combined into one circuit if a high pass L match is used. For this transformation ratio sets the Q to 3.4 and the L match element value becomes L1 is equal to 2.3 NH and C1 is equal to 11.7 picofarads. Class A amplifier. Design examples. The inductor of the L match can be combined with the tank inductor to yield the completed circuit shown in figure, that is 1 volt class A amplifier. Although some effort is required to build an inductor as small as 0.6 nanohertz with loss, good accuracy, and repeatability. The two transistors can be connected together directly or through another RF choke, and the signal to be amplified coupled to the circuit through another DC blocking capacitor. The power consumed by the biasing circuit can be made suitably small by choosing a sufficiently large values of n. More complete 1 watt class A amplifier. If we consider only single-ended implementations, then class A, B, B and C amplifiers look extremely similar, with conduction angle being the only difference. Hence, the output network is exactly the same for all three, including the choke and the output filter values. So, a single design example will sufficient. For the class AB amplifier, the reference bias would result in conduction through less than 360 degrees but more than 180 degrees. Therefore, the drain current of the output transistor would have a quiescent value of less than 825 milliamperes. Since the input drive amplitude must then increase to give us the same output amplitude as in the class A case. The gain is obviously smaller than for the class A amplifier. In the class B amplifier, the bias is supposed to provide a 180 degrees conduction angle. In a case C power amplifier, the gate bias is arranged to cause the transistor to conduct less than half the time. The Class C power amplifier design uses a zero gate bias and increase the drive amplitude to get the desired output power and accept whatever conduction angle gain and efficiency result. In this case, a resistor would be tied between the gate terminal and ground as shown in figure. Although a MOS transistor is shown here, an ordinary resistor may also be used. 1 volt class C amplifier block diagram M1 M2. The inductor value should be greater than 6.4 nano henry to 32 picofarads, 0.6 nano henry 11.7 picofarads. All the values should be like this for class A B C design amplifier.